All right, so the plan for today is to finish up one last problem in section 11.9, representing functions as power series, and then start into 11.10, kind of a strange number for a math textbook, but 11.10, Taylor and Maclaurin series. Note that the Unit 3 exam week is next week, and the sample Unit 3 exam is available now on WebAssign. So that will cover chapters 10 and 11. And as usual, the actual Unit 3 exam will be very similar to the sample Unit 3 exam. Same setup as the previous two unit exams, the WebAssign and in conjunction with Examity and all of that. So that is next week. And then coming up on Wednesday, we're going to finish up chapter 11. And then our last couple of classes will be on chapter 12, starting into the three-dimensional coordinate system. Note that on Wednesday, the 8th, there's an optional review session from 1 to 3 p.m. Again, I'll treat this more like office hours. If you want to pop in anytime, I'll have the regular class Zoom link open. And if we get more than one or two people come in, then we can kind of treat it more like a review session. So it can be kind of office hours, kind of a review session, whatever works best. And then again, the week of Friday 5/3 through Friday 5/10 is final exam week. The final exam will be taken on a WebAssign using Examity, just like the unit exams. Sample exam will be posted in the near future, and you may use a formula sheet. So you can write out your own formula sheet front and back. You can use like that flow chart or anything that you want. A sheet, formula, notes, anything like that can be on there. That's fine. The quote of the day for today, we had talked earlier in the semester about margin, but just to kind of to remind you of that, now that we're getting toward the end of the semester, quote from an author, Michael Hyatt: "You must create more margin so you have room for what's important, not merely urgent." I haven't read any of his books, but I like the quote though. So, and as I kind of mentioned earlier, I find myself when I build some extra margin in, if I leave the house 5 minutes early for somewhere I need to drive to, like I'm much less frustrated, less stressed out, less chance of me being there late or something going wrong. And I think that applies to especially times like this when it's just such a crunch time for both faculty and students, but for you guys especially, where you have exams and presentations and papers and things kind of all due right around the same time. It can be really difficult. And sometimes just making, one or two different choices over these next few weeks can make your life just a lot easier and a lot less stressful. So saying no to that one social event that you really want to go to so that you can, spend that 4 hours knocking out a paper or something and just getting ahead of the work. When you're behind the work and you're kind of on your heels, some people say, oh, that's great because it's a great motivator, but that can also be very stressful. It can be very risky if something goes wrong with technology or something and you're up and right at the last minute to the due date. Sometimes that doesn't work so great. So with both the Unit 3 exam and with the final exam, make sure that you get in, that you complete those exams with a good bit of margin. You don't want to take that big of a chance with a big assessment like that. Okay, so moving on to the material for today. So one last problem in 11.9. We want to compute this integral as a power series. So we might recognize this integral of e to the x squared. It was one of the ones that it's a classic integral that you can't write the integral in terms of nice functions. So you can't write this integral in terms of sines or cosines or exponentials or finite polynomials, anything like that. So if we can't write the integral that way, but if we're kind of searching through those lists of functions and combinations and compositions of them for a function representation of this integral, we're kind of narrowing our vision a little bit, right? Can we search in a bigger function space in a sense? So those things like sines and cosines and exponentials have power series representations, but there are other functions that there are other power series that don't have nice correspondences to exponentials or sines or cosines, or these nice, what are sometimes called closed form functions. And that's our goal here. So our goal is to write this integral as a power series. Where can I start with this? Well, where I can maybe start is I want integral of e to the x squared dx. And I actually know how to write e to the x as a power series. We learned that last time. And this had radius of convergence infinity. It converges on the whole real line. So super nice function. Super nice power series representation, converges on the whole real line. So then what would e to the x squared be? Well, this would be x squared to the n power, which would just be x to the 2n power over n factorial. So I could ask, okay, what if I integrate e to the x squared, but as a power series? And remember that I had a theorem that said if I'm on my radius of convergence, which I certainly am because it's the whole real line, if I'm on my radius of convergence, then essentially I can flip the integral sign and the summation sign. I can move the integral sign inside the summation more or less. Like that. And this gives me this power series representation for the integral. Now, again, of course, we don't recognize this as a power series that is one that we saw before, like a geometric series or something. As I said, this integral doesn't have a nice closed form representation, but we can actually represent it in a power series like that. If we wanted the value of the definite integral, we saw last time that we could get that value by, say, evaluating the series at two different points and then getting some approximation for the series and then an approximation for the integral. So if we have the integral of a function, if we can write that function as a power series, then on its interval of convergence, we can do that integral if we're willing to accept the value of that integral as a power series. So we can get kind of explicit indefinite integrals if we're willing to accept a power series solution as a result. Now, of course, there are lots of integrals where you can get a nice function out, so we probably would prefer that if we were able to get a nice function out, but this gives us kind of a wider range of functions to search through for our indefinite integral results. Any questions on 11.9 representing functions as power series? All right, so that was the last problem in 11.9. We're going to move on to 11.10, Taylor and Maclaurin series. And these are kind of special types of power series. So our goal, we want to directly compute a power series representation centered at A for a function f of x. In other words, we want to represent f of x as a power series like this. We've seen some tricks before. If we could make it look like a geometric series, we could leverage that knowledge that we have, or we use some information from differential equations to get to get this formula. And then we could, make our function kind of fit into that mold, and we were able to figure that out. We maybe even could use differential equations to get power series representations for, say, sine and cosine. But what if I wanted a method to do this for really any function? I don't want to have to look at the specific function and come up with a method that I figure out, whether it's using differential equations or geometric series or something else. I want a method that I can essentially just plug in the function, and this just constructively creates a power series for me. That's what Taylor-Maclaurin series do. Okay, so I want f of x equals sum n equals 0 to infinity cn times x minus a to the n. Well, one thing is that if I want my function to be equal to this power series, it has to equal this power series at all points x. Well, particularly at the center. So maybe I can start off by saying, all right, well, I know that this series is, I know that it's c naught plus c1 x minus a plus c2 x minus a squared. I'll do a couple more. Okay. Well, if I plug in x equals a, on the left side, I just get f of a. That's the center of my power series. I better converge there. If I plug in x equals a, then everything from the c1, c2, and so on term all go away, and I just get c naught. Okay, that's kind of cool. I guess I figured out what one of my constants has to be. The constant c naught has to be f of a. So if I know what my function is that I'm interested in finding a power series representation for, I can get the constant term. I plug in the center of the power series into f. I get f of a, that's some number, and that's what c naught has to be. Okay, I mean, that's not super helpful. I have a whole bunch of CIs that I have to find. But maybe another thing that I realize is that if I can differentiate f, then I can differentiate the power series at the center. So what would f prime of x be? Well, c naught goes away, it's constant. c1 times x minus a differentiates to c1. Next, we get 2c2 x minus a, 3c3 x minus a squared, 4c4 x minus a cubed, and so on. So that's f prime of x. That's the derivative. As long as I'm on my interval of convergence and the center is right in the middle of the interval of convergence, this is a fine thing to do. I could then compute f prime of a. So if I plug in a into the left side of this formula, that's f prime of a, that's going to be some output of my function, provided my function is differentiable, of course. On the right side, I noticed that the 2c2 and 3c3 and all of these terms have x minus a in them. So when I plug in a, they all go away. I'm just left with c1. So f prime of a is c1. I see that as I differentiating helps me kind of pluck out one specific term, differentiating, then plugging in the center. So what if I take the second derivative? We might at this point think that, oh, is ci just the ith derivative at a? Not exactly. If I take one more derivative, the c1 differentiates to 0. 2c2 x minus a differentiates to 2c2. 3c3 x minus a squared differentiates to 3 times 2 c3 x minus a to the first. 4c4 x minus a cubed differentiates to 4 times 3 c4 x minus a squared, and so on. For my second derivative, if I plug in a on the left, again, provided I can differentiate the function f and plug in a, f double prime of a is what I get on the left, and on the right, the C3 bit, the C4 bit, and so on all have a factor of x minus a in them. So when I plug in x equals a, they all go away. I'm left with 2C2. Or in other words, f double prime of a over 2 equals C2. So it's not quite that Ci is the ith derivative at the center. There's a little extra going on here. Let's do one more and see if we can see the pattern. We might see the pattern already. Let's do the third derivative. The 2C2 goes away. 3 times 2 times C3, x minus a differentiates to 1. So this is going to be 3 times 2. I suppose we could write a 1 here. That wouldn't hurt anything. C3. That's kind of like the 1 coming down almost. I can differentiate here. I get a 4 times 3 times 2, C4, x minus a to the first, and so on. My third derivative at a, on one hand, is just f triple prime at a, some number. On the other hand, this is the only constant left over. These all have an x minus a in them. They all go away when I plug in x equals a. 3 times 2 times 1, C3. Well, but I actually see that that's like 3 factorial C3, right? And I see that this is going to end up in the next line being 4 factorial. That's already 4 factorial, I suppose, but this 1 will come down, get rid of the x minus a, we'll have 4, 3, 2, 1. We can imagine that the next one is going to be 5 factorial, 6 factorial. Once we differentiate far enough to turn a term into a constant, it's just going to have its original power with a factorial. So f triple prime is 3 factorial C3, or f triple prime at a over 3 factorial is C3. And I see that this does, if I think of factorials, 2 is just 2 factorial. I mean, I could have written this. I could have said like there's a 1 there, kind of pulled that 1 down. This could have been a 2 times 1 C2, so 2 factorial is just 2. Of course, C1, this could be 1 times C1 or 1 factorial times C1. And C0 is 0 factorial. 0 factorial we define to be 1 for many reasons, and it makes a lot of these formulas just come out nicely. So we really see that C sub k is the kth derivative of f over k factorial, where k is a natural number. This, of course, presumes that we can differentiate our function f and evaluate those derivatives at a. One thing that's actually really interesting, I think, so just here is written a little more cleanly. One thing that I think is really interesting is there's this idea of different levels of infinity, right? Some infinities are bigger than others. So there are like counting numbers like 1, 2, 3, 4, 5. There can be infinitely many of them because the list never ends. But you can always say like what the next one is, right? Like if you're at 5, what's the next one at 6? If you're at 6, what's the next one at 7? And the somewhat related idea, this isn't exactly mathematically precise, but to give you kind of something like an idea, in the real numbers, if you thought of the open interval, say 0 to 1, like what's the first number there? Well, there's not really a first number, right? Any number that you say that's in the open interval 0 to 1 could, somebody could pick half of that number, and that would also be in that open interval and would be smaller. Or like if you say the number 1/2, what's the next number in the interval for 1/2? Well, that doesn't really make sense to ask in that context. So this kind of hints at the idea that there might be different kinds of affinities. Again, that's not exactly um, the right notion. That's more the notion of density, um, but I think that's kind of the easiest way to at least hint at the idea that there are different levels of affinity. So in a sense, f of x, if I write like f of x equals x squared or something, there's this kind of higher level, this uncountable infinity of inputs and outputs. Like when I write f of x equals x squared, that encapsulates uncountably infinitely much information, right? I can plug in any of the real number values into that and get an output. How much information do I need to write out my power series? Well, interestingly, there's like a first bit of information I need, C naught. There's a next bit of information, C1. There's a next bit of information, C2. I only need countable much information, so to speak, to be able to write out my power series. I maybe this is a little abstract, but it's almost like a little bit of mathematical magic in the sense that we seem to get a whole bunch for free. We kind of we're really leveraging heavily this polynomial basis, and it really lets us extract, in a sense, like infinitely more information than it maybe it, as a gut feeling, feels like we ought to be able to with the knowledge that we have. If we know just the derivatives of the function at a certain point, we can then say anything we want to say about the function. I mean, provided that it differentiates and converges and all of that good stuff. If I know just the value of the function at a, its first derivative, all of its derivatives at a, then I can say anything that I want to know about that function anywhere, not just at a, but at anywhere. I can, if you say that the power series is centered at 3, and you give me all of the derivatives at 3, I could tell you what the value at 1,000 is, or negative 1,000,000, or whatever. It almost feels like cheating somehow that we get so much for free. So this is a Taylor series. We take our function and we write it as a power series where the coefficients are the nth derivative of f at a over n factorial. As kind of an aside, that n factorial on the bottom, that really helps things converge, right? We've seen in the past that like when there's an n factorial on the bottom, we tend to get very nice convergence. I mean, we could come up with examples that are pathological where we don't get convergence, but we tend to get very nice convergence when there's an n factorial on the bottom, because that denominator just grows so quickly as n increases. What's a Maclaurin series? Well, Maclaurin series is just the Taylor series centered at a equals 0, a fairly common place to center our series. So Maclaurin series is just sum of the nth derivatives at 0 over n factorial times x to the n. And both of these, of course, these equalities are only valid on the open interval of convergence. Okay, so let's actually look at an example here. Let's look at f of x equals e to the x. And we've already found a power series representation for this, but let's try to find another one, or we'll try to find the same power series representation, but another way. Let's take a different approach. Instead of taking the differential equations approach, which was very ad hoc, where I said I kind of understand how to work with power series related to differential equations because of some theorems I had. And I also know that e to the x works really nice with some simple differential equations. And I was able to marry those two ideas together to get a power series representation for e to the x. Now that I have this idea, can I do this more constructively in a way that's more just systematic and doesn't require as much ingenuity or ad hoc work? Well, let's try. So I want to say that e to the x is sum n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the n. Well, of course, f of x equals e to the x. F of 0, e to the 0 is 1. Its derivative is itself. So its derivative at 0 is also 1. And of course, since its derivative is itself, its second derivative is itself, its third, and so on, all of its derivatives are just 1. So really just in general, the nth derivative at 0 is going to be 1, or we just have x to the n over n factorial, and we actually just get it in one line. I mean, after we did this work to show why this is a reasonable thing to do, but we get the answer in one line, right? In the differential equations approach, we did a lot more work than this. Let's look at them. Oh, and sorry. Also, let's find the Taylor series representation for the same function centered at a equals 1 to finish up this problem. So here I want the derivative at 1 over n factorial times x minus 1 to the n. So these have to match up. It's very important that my derivatives are at the center of the series, right? If we try to do it a different way, this construction would fail. It was very important that where I plug in my inputs are at the center of the series, because that's what makes that whole tail disappear for each of the derivatives. Well, of course, I know that f of x is e to the x. F of 1 is just e to the 1. And of course, f prime of 1 will be e, and the nth derivative at 1 will be e. And so this is the sum from n equals 0 to infinity of e over n factorial, that's the coefficient, times x minus 1 to the n. Maybe not one that looks as, as nice or as simple as this one here. But if we wanted a power series representation centered at 1, this would do the trick. Okay, so let's look at f of x equals 1 over 1 plus x squared. And in particular, we're going to look at the symmetries of our function f and the symmetries of the Maclaurin series. All right, so what can I do here? I can say, well, first, let's say f of x 1 over 1 plus x squared. We want to be sum n equals 0 to infinity, derivative at 0 over n factorial times x to the n. So what's f of 0? It's going to be 1. And then, well, f of x is 1 over 1 plus x squared, or 1 plus x squared to the minus 1. So what's the derivative going to be? What's f prime of x? It's going to be minus 1 times stuff to the minus 2. And then chain rule times the derivative of the stuff 2x. What's f prime of 0? Well, that 2x that popped out is going to make that a 0. What's the second derivative? Well, the second derivative is going to be, I have a product. So first times the derivative of the second. So there's first times the derivative of the second. And then plus the second times the derivative of the first. -2 is going to come down. One plus x squared to the -3 times 2x. What's the second derivative at 0? Well, this second term, this one here, is going to be 0 when I plug in x equals 0. But my first term, when I plug in x equals 0, I have 1 to the -2, which is just 1. It's going to be -2. Let's do maybe 2 more. Maybe 1 more, maybe 2 more. We'll see how tired I get of doing derivatives. All right, if I start with just the first term in the second derivative. So this is -2. Then I differentiate, I get a -2. 1 plus x squared to the -3 times 2x. My second term, let me rewrite this a little more cleanly. So I have 8x squared, 1 plus x squared to the -3 power. So if I differentiate this, I have to differentiate the first. 16x, 1 plus x squared to the -3. So that's differentiating the first, keeping the second, and then plus, keep the first, differentiate the second. And I get that. And I noticed that for this third derivative, I have 3 terms. Each term has at least one factor of x by itself. When I plug in 0, I get 0 out. And let's do one more. All right, so this first term from these 3 is going to be what? -2 times -2 times +2 is 8x, 1 plus x squared to the -3. That's what that term simplifies to. When I differentiate that, I differentiate the first bit here. I get 8, 1 plus x squared to the -3. So that's differentiating the first, keeping the second, plus keep the first, differentiate the second. And then for each of these down here, okay. Okay, I do have to go. Okay, I'm just double checking my work here. Yeah, okay, looks good. I was a little worried about the 16x. I was thinking that should have been an x squared, but I had 2 factors of x, differentiated it down to 1, so it looks good. If I look at this one, I have 16x. I differentiate that, I get 16 times the second bit. And then I keep the first, differentiate the second. So that's for that term. And then this term, I see that when I combine these two together, I'm going to get a cubed, x cubed. When I differentiate that, I'm going to get 3x squared times some stuff. plus, then I'm going to have an x cubed times some stuff. And when I plug in 0 into the fourth derivative, well, this bit goes away, this goes away, both of those go away, but both of these stick around. So it looks like I'm going to have 24, I think. So I might notice a couple patterns here. I know that was quite a bit of work, but if I look at the patterns, I note that the odd derivatives go to 0 and the even derivatives stick around. I note that for the even derivatives, the sign flips. And I might notice that 24 is 4 factorial, that minus 2 is minus 2 factorial, that 1 is 0 factorial. So it looks like the sign flips for the evens, and it looks like I get the factorial related to the derivative. It looks like the factorial is going to cancel, and I'm going to get minus 1 to the n, x to the n, but only for the evens. And it looks like the odds are all going to go away. So it looks like I get something like that from this pattern that I recognized over here. As an aside, remember, I actually could write this as a geometric series, 1 over 1 minus negative x squared. And I know that this is going to, 1 over 1 minus x is sum of x to the n. So this is going to be negative x squared all to the n, or negative 1 to the n, x squared to the n, or x to the 2n. So this does look right. So the pattern that I pulled out over here does seem to be the right pattern to continue with. Or this is going to be like, what is it going to be? 1 minus x squared plus x to the fourth minus x to the sixth, and so on. So something interesting, if we think back to symmetries of functions, we would look at this function and we would say, well, f of x equals f of negative x. And we called this an even function for some strange reason in Calc 1 or in pre-calc. And other functions, we might have that f of negative x equals negative f of x, where the negative kind of comes out. That doesn't apply to this function, but it could apply to other functions. And we called those odd functions for, again, some strange reason, some odd reason. Well, now maybe we see a little more clearly this 1 over 1 plus x squared is an even function. Its power series representation only has even powers. For f of x to equal f of negative x, when I write out its power series representation, I need to get rid of all the negative signs to have the same function left over. Only the even powers do that. The odd powers would let the negative sign come out, and that would change the power series representation. So even function, it's called an even function because its power series representation has even powers, has only even powers. Something like, say, sine of x that we know is an odd function, f of negative x equals negative f of x, or it flips over the y and x axes instead of just the y axis. Or in other words, negative signs can just come out of the function. Well, these odd functions, their power series representation will only have odd powers. So then when we have an x cubed or an x to the fifth or an x to the 11th or something, when I make that a negative x cubed or a negative x to the fifth or negative x to the 11th, the negative just comes out of every term in the power series, and it effectively just gets factored out. So it's kind of interesting that we finally see why we have these strange names for symmetric functions, even functions and odd functions, because of their power series representations. Even functions like this one, all of the odd derivatives turn out to be 0. The odd derivatives at 0 turn out to be 0. And the representation only is left with the even powers. Note that an odd function evaluated at 0 has to be 0. It can't be an odd function otherwise. If it's allowed to be evaluated at 0, f of 0 has to be 0 for it to be an odd function. And the derivative of an even function is odd. The derivative of an odd is even. The derivative of even is odd, right? So that's really what's kind of going on behind the scenes. When we take derivatives, even functions switch to odd and odd switch back to even. So that's why and like I said, the odd function evaluated at 0 has to be 0 for this property to hold. So that's really what's kind of going on a little more deeply behind the scenes, is we keep switching our even function into an odd, evaluating at 0, that has to 0 out. Back to an even for the next derivative, but back to an odd for the one after that, that has to 0 out, and so on. So it's kind of interesting that we really see that symmetry of some of these functions and the way that they work is really kind of deeply embedded in their power series and Maclaurin series representations. Any questions so far? All right, so Taylor series and Maclaurin series, I mean, kind of nice ideas. And but one super nice thing about Taylor-Maclaurin series is not only do we get a method for constructing a power series, but if we ever actually want to use this power series, I mean, maybe it's kind of nice philosophically to know that I could write e to the x that way, or that I could write 1 over 1 plus x squared this way. Maybe that's kind of nice, but if I ever actually want to compute anything with these, if I ever want to solve a real world or a tangible problem, I need to get a number out. I need to be able to do f of, or I almost said like f of 3, but this guy only converges on -1 to 1. So I need to be able to evaluate maybe f of a half. And I mean, it turns out that this is an alternating series, so we kind of got lucky there. Maybe we could apply alternating series estimation theorem and get an idea of what our error bounds are and how far we need to go in the series for certain accuracy. But something like this, I mean, if we wanted to do e to the first power, how many terms do I need to compute to be at the level of accuracy or precision that I need? I don't really know right now. So it's nice that I could write e to the x this way, but I would like to be able to figure out e to the 1 or e to the 5 or something like that. Well, nicely enough, we have Taylor's theorem and kind of two Taylor's theorems. So the first is that suppose that we write our function as its Taylor series representation, but just the kth partial sum plus the remainder, right? So that's just like taking this summation here and breaking it into two sums, sum n equals 0 to k of stuff, plus sum k equals 0 to infinity of stuff. This is what we're calling tk, the kth partial sum of the Taylor series. And this is rk, the remainder. So suppose I do this, I pull off the kth partial sum of the Taylor series from the front. That leaves over a remainder for the tail. Then we can say if limit as k goes to infinity of rk of x is 0 for absolute x minus k less than r, x minus a less than r, then we say that the Taylor series equals the function on that interval. So this is something that we've been maybe a little bit not super careful about, is I've been saying equals here, or I've been saying equals here, But we haven't been really careful, have we? Right? We really should at this point have gone through and done the ratio test, and then we can show that the radius of convergence is infinity. I kind of mentioned it up here, I think, but we had seen that before, but I didn't really do that explicitly. In order to say these two sides are equals, I really ought to say what the radius of convergence or the interval of convergence are. And that's very important down here, where my interval of convergence is only open -1 to 1. But what we're saying is that we have a theorem here that if the limit of the remainder is 0 in a certain open interval, then the Taylor series equals the function on that interval. We have another theorem that, from maybe an applied perspective, is very, very nice. Taylor's inequality. And that's the following: that the remainder in absolute value is bounded above by something. So remember the partial sum tk looks like the n equals 0 term. It looks like what? Oh, not x minus a. Sorry, my dog's barking in the background. So the n equals 0 term, the n equals 1 term, 0 factorial, 1 factorial, x minus a, and all the way out through the kth derivative term. This all is tk. And then the first term for the remainder is the k plus first derivative term. And let me just get rid of a bit of this over here. And then some other stuff. But what I really want to point out is the first term of the remainder. In other words, the first term we leave off from our partial sum is the k plus first term that looks like the k plus first derivative at a over k plus 1 factorial times x minus a to the k plus 1. The remainder in absolute value is less than or equal to something that looks like 1 over n plus 1 factorial times something like x minus a to the n plus 1. What do we use on our numerator instead of the k plus first derivative at a? Well, we have to use kind of the worst case for the k plus first derivative on this interval. But if I have a constrained interval over which I'm looking to evaluate this function, I can ask what is a number that bounds the n plus first derivative above in absolute value. If I can find an upper bound for the n plus first derivative on this interval, then I can bound the remainder in absolute value. I can bound the error. And the error is bounded above by something that looks kind of qualitatively like the first term we leave off. It has a feeling of the alternating series estimation theorem. The alternating series estimation theorem said if some criteria are satisfied, our error is bounded in absolute value by the first term we leave off. And that's kind of what we're saying here, with the one caveat that we need to use kind of the worst case for that next derivative, the maximum value for that next derivative over the interval that we're interested in. But Taylor's inequality has a similar feel to the alternating series estimation theorem. There are some common Maclaurin series that pop up a lot. The binomial series, 1 plus x to the k equals 1 plus kx plus k times k minus 1 over 2 factorial x squared, and so on. If k is a positive integer, this actually terminates. K choose n will equal 0 after a while, and the series terminates, and we get just kind of the binomial expansion. But we can actually generalize this to real values of k. So for instance, 1 over 1 plus x, we could think of as 1 plus x to the minus 1 power, which is 1 minus x plus x squared, and so on. Or 1 over root 1 plus x is 1 plus x to the minus 1/2 power. This is going to look like 1 minus a half x plus a quadratic term, and so on. Or actually, 1 over root 1 minus x looks like 1 plus a half x plus quadratic and so on terms. This actually comes up in special relativity. So sometimes you want this kind of linear component to add a correction in, but maybe you don't need the quadratic component. Maybe that's sufficiently small that you just need the linear component. Or maybe you need the quadratic component, but not the cubic. So in applications like, physics or engineering, you kind of use enough terms where, the more terms you use, the more complicated it gets, but the more accurate you get. So you use enough terms to reach the accuracy you need, but no more than needed for the accuracy that you need for that problem. So you see these kind of things, Maclaurin series and Taylor series, come up all the time in physics and engineering and the applied sciences, where they'd rather deal with an approximation that's a very good approximation, but maybe not the full function, because the full nonlinear function might be really annoying to deal with, but say a linearization or a quadratic or a cubic approximation might work well enough for their purposes and keep the problem simple enough that it can be solved reasonably well. So some common Maclaurin series, one that we've seen already, of course, is the geometric series that kind of started this whole discussion with a radius of convergence of 1. One that we've seen derived a couple different ways now is for the exponential function, some x to the n over n factorial, radius of convergence infinity. It converges on the whole real line. Sine and cosine have these power series representations. Note that sine of x is an odd function in the sense that sine of negative x equals negative sine x, or in the sense that it's symmetric about a 180-degree rotation about the origin, or it's symmetric if you flip over x then y axes. And note that it only has odd powers, x to the power 2n plus 1. For cosine of x, we know cosine is an even function. It's symmetric about the y-axis. It has, if I can select it, only even powers. We notice actually that it almost looks like if we kind of were to somehow like add sine x and cos x together, that we would kind of get like all of the powers, and it might look a bit like e to the x. And it actually turns out, we'll do this next time, we don't have enough time today, but it turns out that something like that is true, but we need to move into complex numbers. So we don't really talk about complex numbers much at all in this course, but for this example, we'll just demonstrate this identity. And then for the log of 1 plus x has this power series representation. Of course, we don't expect an infinite or even very large radius of convergence here because, well, we can't log 0 or negative numbers. So the best we could really hope for on the left side is that x goes down to -1, and we do indeed get a radius of convergence of 1. So about the best we could hope for. If you want to work out sine and cosine's power series representation, I mentioned last time that you could do it through the differential equations approach like we did for the exponentials. I think it's kind of a fun exercise to do. You would have to think about what are your initial conditions. You'll need one for the function, say at 0, and one for its derivative at 0. So you'll need 2 initial conditions. you could also use the Maclaurin series formula from up here, wherever it was. You could also use this formula. And of course, with sine and cosine, with their derivatives being cyclic, you'll be able to figure out what the coefficients for each of these powers is going to be. And for the log, so you could do these either way. It might be good practice to do it both ways even. And for the log, of course, you could just plug that into the Maclaurin series formula. And the derivative is going to be like 1 over 1 plus x. And you can use Maclaurin series directly, or you can say, well, if the derivative is 1 over 1 plus x, but I know how to write the derivative as a geometric series, can I back my way into what the original function's power series representation should be? So you could also approach this one maybe 2 different ways. All right, any questions on anything we talked about today?